Hello, my dear students, and I'm coming to you from my iPad to begin our discussion of Chapter 2 from your book. I'd like to break our discussion of Chapter 2 into 3 lectures, basically 3 days or a week and a half of work. I'll have a little assignment for each portion, so there'll be 3 exercises accompanying this chapter. It's a rather lengthy and busy chapter in the sense that it covers all kinds of things, atoms, molecules, and ions. And I'd like to start with a little chemical history of the atom and then stop after about 20 slides and then start again and talk about elements and then stop again and talk about putting those elements together to make molecules and compounds. So any good student of chemistry should know about Dalton. John Dalton, an Englishman. He was an incredible mind. He was a Quaker and so was rather excluded from the traditional colleges and universities, which historically have always been associated with the church. In the case of England, I guess the Anglican or Church of England, depending on who the ruler was at the time. I don't claim to understand everything about it, but he taught at, I guess you would say, alternative schools. Quaker schools. He actually started teaching high school at age 11. And at same school, he worked his way up to principal from age 19 to 26. He was principal of the school, and he did a lot of work. He was actually a math teacher, though he also taught natural philosophy, or what we would call natural sciences or physical science. And after a while, he moved and went to a university in Manchester. Again, kind of an alternative one, not associated with the Church of England. That is where he did a lot of research in meteorology, color blindness. He and male members of his family were colorblind. And in fact, color blindness used to be referred to as Daltonism. Anyway, John Dalton lived from, and you don't have to know these dates, but 1766 to 1844. So that would make him what? 77, 78 years old when he died. But he came up with our modern theory or modern atomic theory of matter. And we owe a lot to him. Basically, his theory says that every element, every pure element, is composed of extremely small particles called atoms. Now, we got the term atom from Democritus, who lived around 400 BC. And we don't know how he pronounced it. We don't know how ancient Greek was pronounced, but he came up with the term atomos, or atom, for us. And said that at some point, if you keep subdividing matter and subdividing it, you'll get down to a particle called an atom. And after that, the matter can no longer be subdivided. And his theory says that atoms of one element are all identical. That the atoms of an element, say gold, are all gold atoms, and the atoms of the element oxygen are all oxygen atoms. And they're all identical to one another, and if they're different, then you have a different element. Or he also said that atoms of different elements differ in their properties, and we'll talk about what those properties are. So, atoms of a given element are all identical, and you can't change them into from one element to another, and also that you create new substances by linking or separating these atoms together and linking them together and separating them apart, then but the atoms themselves always retain their character, and the atoms can neither be created nor destroyed. Now we're going to talk about how this quite acceptable, good modern atomic theory now has some caveats associated with it and some conditions. But, for example, we now know that atoms can be created and destroyed. We know that atoms can be changed from one element to another through nuclear chemistry. And we also know that they can be subdivided because, of course, we know they're made up of protons, electrons, and neutrons. But it doesn't change Dalton's postulates, Dalton's theories, because we do still believe the fundamental truth, and that is an atom is the smallest particle of matter that retains the properties of that matter. And finally, he said, when you do combine these and you combine them in different ways, you form different compounds. But that a given compound always has the same relative number and kind of atoms. Dalton gave us many things. Not just chemistry, but like I said, meteorology and color blindness. And he was a general scientist with lots of interest, but we have several laws. We have Dalton's law of partial pressures. We have a gas law. He even gave his name, or we've used his name to describe a unit in chemistry. So you'll be hearing his name a lot. Dalton's law of conservation of mass says that the total mass of the reactants in a chemical reaction equals the total mass of the products that are produced in that chemical reaction. Another way you've heard this stated is matter can neither be created nor destroyed. Something we qualify now when we talk about nuclear reactions. So that's Dalton's law of conservation of mass, and he has another law, very famous law of multiple proportions. It says that when two elements come together to form a compound, they do so in small whole number ratios. Now, he didn't know everything we know today, but he was making different compounds like carbon monoxide and carbon dioxide. Carbon monoxide is carbon and oxygen, and carbon dioxide is carbon combined with two oxygens. And he saw that every time he took 12 grams of carbon, for example, and 32 grams of oxygen, according to his first law, he got, what's 12 and 32? 44 grams of CO2. But he also saw that if he took different amounts, for example, half as much, 6 grams of carbon, it combined with half as much oxygen, 16 grams of oxygen, to give half as much, or 22 grams of CO2. So he saw that there were always these small whole number ratios where these atoms combine to form different compounds. And that's his law of multiple proportions. Two or more compounds can exist from the same element. Another good example is water and hydrogen peroxide, H2O and H2O2. But they can't have the same relative number of atoms. If they do, then they're the same compound. If they're different compounds, then they have different relative numbers of atoms. So we now know that his little rule about atoms of, an element are the smallest indivisible structure or particle. They are the smallest, an atom is the smallest particle possible that retains the properties of that element, but we now know that they can be subdivided into electrons, neutrons, and protons. And this was, his discoveries were done before some of these other people discovered these subatomic particles we're going to move into next. And the first one to be discovered was the electron. And J.J. Thomson, in 1897, he lived from the 1850s all the way up to, I want to say, 1940, almost to World War II. He was working with cathode ray tubes that are tubes. You put a charge across it. These two electrodes are connected to a high voltage source, and you see a flow of particles from one electrode to the other, from the cathode to the anode, to the positively charged anode in this case. And if you put a fluorescent screen in there, those particles will hit the screen and cause the fluorescent chemicals to glow. So you can actually visualize this. And he also saw that it was affected by magnetic fields and ascribed to them a negative charge, that these are negatively charged particles, invisible particles that you cannot see. And we know cathode ray tubes from our old-fashioned big TVs and old-fashioned computer monitors. But he was not able to determine the charge or the mass of these particles, but he was able to calculate the charge to mass ratio. And this is it here. He measured it fairly accurately to 1.76 times 10 to the 8th coulombs per gram of particle. But all he could get was the charge to mass ratio. Robert Millikan, working at the University of Chicago in around 1909, did his famous oil drop experiment where he took a mist, a very fine mist of oil drops, and put them in an electric field and charged them with x-rays. And he noticed that the charge was always a multiple of 1.6, you don't need to know this, of course, times 10 to the minus 19th coulombs. So he deduced the charge on an electron as being 1.6. We now know it's 1.6. He measured it as 1.59, but 1.602176634 times 10 to the minus 19th coulombs, a measure of charge. And since J.J. Thomson had the charge to mass ratio, 1.76 times 10 to the 8th coulombs per gram, and Millikan deduced the charge on a single particle, 1.6 times 10 to the minus 19th coulombs, they were able to then calculate the mass of an electron. And if you use modern measurements and modern technology, I think he measured 9.2 or something, but it is 9.10938215 times 10 to the minus 31st kilograms. So that's 9.109 times 10 to the minus 31. Sorry, but my pencil doesn't write well on this. Kilograms. That's a tiny, tiny substance. And this also emphasizes what I was telling you about the nature of chemistry. We need to use scientific notation because we work with atoms and particles that are extremely small, and we need scientific notation because I'm not writing 31 zeros in front of these numbers. And because they're so small, if we work even with a thimbleful or a dot of these particles, we're working with incredibly large numbers of particles that are incredibly small in size. Anyway, we now know the size of our electron. It takes about 1,800 of them to equal one of the protons or neutrons. So we usually don't consider their mass when we're talking about atomic masses, but they do have a very small amount of mass. Now, I want to introduce radioactivity only briefly because we employed radioactive techniques to study the atom. And you can, in second semester, if you have the time and get to it, you will get a brief chapter and maybe a week if you're lucky of nuclear chemistry. But if you go on in chemistry, you can take individual courses in nuclear chemistry and nuclear physics and physical chemistry and quantum chemistry. Anyway, radiation is the spontaneous emission of high-energy radiation by an atom. First observed by Henri Becquerel, but Marie and Pierre Curie studied it, by the way. Madame Curie, Marie Curie, is one of only 3 people I know of who's actually earned 2 Nobel Prizes, one in chemistry and one in physics. But basically, there are 3 types of radiation. Alpha particles are huge. In comparison, they're basically 2 protons and 2 neutrons, or a helium atom's nucleus. But because they're so big, they're very slow and they can't penetrate even a sheet of paper. Beta particles, they shouldn't really say negatively charged, but they are charged. 99% are negatively charged like electrons, but it could be a positron or some other unusual subatomic particles. But in general, beta particles are electrons that can penetrate, a few inches, a few centimeters of air, and can't really penetrate your skin either. And the danger for all of these is not so much the radiation as ingestion and them being taken up into your body. Gamma rays are high-energy photons, uncharged but carrying tremendous energy, and can travel several meters through air and frequently require shielding, like what? Like lead or plexiglass or, thicker shielding to protect you so you can work with it. Anyway, Rutherford was working with alpha particle emitters, some elements like certain forms of bismuth or radium and radon and actinium and uranium and thorium. In the lab, I used to use thorium, which is commonly found in Coleman lantern mantles, but they stopped making them with thorium. So you have to find old Coleman lantern mantles just for a good alpha particle source now. But up until this time, J.J. Thomson knew there were electrons, and he knew that those negatively charged electrons needed to be balanced because atoms are neutral, by other positive charges. And he had this plum pudding model where you have this sea of positive charge with the electrons being the plums in the pudding throughout, or the chocolate chip cookie model, or the raisin cookie model. That's not the case. And I don't know why we teach the wrong models before we get to the right models, but Rutherford changed our view on that and gave us what we call a view of the nuclear model of the atom. And what he did was he took a source of alpha particles. I want to say he used thorium, but I'm not sure. And contained inside, for example, a lead block with a hole in it that produced a beam. And remember, these can't even go through a piece of paper. But what they can do is go through a sheet of gold foil, because gold has very unique properties, is extremely malleable, and can be pounded into sheets a few atoms thick. So it only has to go through 3, 4, 5, rows or layers of atoms. And what he found was that 99% of the alpha particles, these huge, slow alpha particles, went through, hit a film strip, and made a big dark spot on the film strip. But occasionally some were deflected, including right back at the particle source. And that told him this, that yes, most of these alpha particles come screaming through this, but occasionally they interact with something that blocks them and repels them and changes their trajectory. And that must have two things. One, it must have a positive charge like the alpha particle. And two, it must be, relative to the space of the entire atom, very small. And that's actually the case. That we have a very small, dense, positive nucleus at the center of the atom with the electrons around it. And he also told him that most of the volume of the, I don't know how to go back. Let's see if I can do it this way. Most of the volume of the atom is empty space for those particles to make it through. And that's exactly the case. Atoms themselves are very small, on the order of a couple of angstroms. An angstrom is an unusual unit. We're not supposed to use it anymore. It is 10 to the minus 10th meters. 1 angstrom equals 10 to the 1 times 10 to the minus 10th meters. This is not an approved SI unit. We're actually supposed to use picometers. So your atom may be very small. 1 angstrom is a typical value, 1 or 2 angstroms. It says 1 to 5 angstroms. It's just inelegant to say 100 to 500 picometers. And most bond lengths are 1 to 2 angstroms. So it's very handy to use angstroms. I'll use them from time to time, but just know that they're not official. So now we have a dense nucleus, and it's made up of protons and neutrons, and they have the following properties. Protons have a positive charge and a approximate mass of 1 atomic mass unit, or a relative mass of 1. A neutron is neutral, has no charge, and essentially the same mass, until you get out to 4 or 5 places, as a proton. An electron has a negative 1 charge, and a charge equal in magnitude but opposite that of the proton, +1 and -1, but a mass that it would take 1,700, 1,800 of these to equal 1 proton. The atomic mass unit is an artificial unit in the sense that it is defined as, depending on whether you're a physicist or a chemist, 1/12 the mass of a carbon-12 atom. We'll get to that in our next lecture. If you're a physicist, it's 1/18 of a oxygen 18 atom. And it's very similar, but not exact. But there's another unit that I learned that's equivalent to the atomic mass unit called the Dalton. So sometimes I'll say Dalton, sometimes I'll say atomic mass units, but in general, I won't use either one, because when we get into the periodic table, I'll show you what those values really mean when we talk about masses as relates to elements and the compounds they form. So, atoms have extremely small masses. They are extremely small, and their size, the size of the nucleus, is much smaller still. So, in going through this history, I want to just let you know this is the view of the atom now. And we can exploit changes in atomic mass. To the point of even telling isotopes apart. I'm going to talk about isotopes next when we talk about the elements. But there is an instrument called a mass spectrometer where a sample is heated to extremely high temperatures to destroy it and ionize it. And the individual atoms, or their ions, which is a charged form of an ion, are moved through a series of charged plates and to be accelerated, and then they pass through a magnetic field, and the more dense ones will not be deflected by the magnetic field. They'll tend to go straighter, and the lighter ones will curve more and be affected greater by the magnetic field. And a detector can tell and measure those differences in mass in this mass spectroscope and give you a spectrogram or a pictorial representation of what types of atoms are present. This is used to identify unknown substances, used in forensics to analyze and identify poisons or drugs or the like. So, I want to stop there. I'll post an assignment, and we will start back with this next part of Chapter 2 in the next talk. So for now, I'll say goodbye. I hope everybody has been able to stay warm, maintain their power, and stay safe. And you will see the next portion of this chapter posted already. As soon as I post this one, I'll post the other ones as well. And I will also, with the assignments, be posting a video guide to how to work them. Goodbye now.